Again, light is a form of electromagnetic radiation. Again, this should be page number, oh, I don't have a page number on that, but probably page 8. Thank you. Electromagnetic radiation can is associated with, well, let me rephrase that. It's a wave. We're going to see that light can behave like a wave, and it can also behave like a particle. That's called the wave-particle duality. So we can describe it like a wave, and in this case, electromagnetic radiation is called a transverse wave, which means it's going to have our typical like wave pattern. It's just like ocean waves, okay? The other type of wave is called a compressional wave, which means that it, like they bump into each other, and you can have compressions and rarefactions. So have you ever been to like a loud concert or, I don't know, I hope you haven't been around a bomb or a cannon or anything like that, but have you, like, can you, have you ever been somewhere where you can feel the sound hitting you? Compressional waves, okay? So it hits you. I do think of like bombs because you can see, like you almost see the energy waves, but the sound also hits you like that. Yes. Yes, I'm sure you felt that compressional wave, okay? One of the reasons why I don't do explosions in my class is because my chemistry teacher did one. He lit ethanol vapor on fire in a Gatorade bottle, and he had a shield up and everything, okay? So, like, he had a shield up, and I was about 2 rows back, and one of the nails that he had used ended up by my foot, and, like, he just happened to put too much in, and that makes it sound like he was a careless chemistry teacher. He wasn't. He was actually a really, really good chemistry teacher. Part of the reason why I am a chemistry teacher to this day. And he even looked at us and was like, whoa, that was not good. And so, because like none of us had goggles on, because we were all sitting down and he was up at the front. And so, like, that was on the first floor. The third floor felt it. So, like, compression, and that's why I was like, if he can mess something up so easily like that, like, I'm scared to try to blow anything up on purpose. So, sorry, you get the lame-o teacher. But anyway, it's a transverse wave, and that means that it can travel through a vacuum, or we could say that it does not require matter. Now, a wave is going to transfer energy. So it carries energy. It's not necessarily energy itself, but it does carry energy. And so in this case, light, all of this electromagnetic radiation will carry energy. Okay. Now, our electromagnetic spectrum goes through lots of different types, and we're going to see that any wave can be measured in what we call a wavelength. Okay, so wavelength, we use a Greek letter lambda, and it looks like an upside down Y. For some reason, it looks like a brontosaurus to me, but it only has 2 legs. But that's what we use for a wavelength. And that is simply going to be the length of the wave from crest to crest. Okay. So if I go up to my example of a wave, this right here would be considered our wavelength. We can also measure waves in terms of frequency. Anybody heard of frequency before? Where have you heard of frequency? Just in science classes? All right, what's your favorite radio station? Nobody listens to a radio station anymore. It's all like 97.1. Okay, so 97.1, what that means is it's 97.1 megahertz, which is the frequency of the sound wave or the radio wave that is actually being transmitted. Okay, so when we talk about radio stations, they are using radio waves and they have a frequency, and that's what those radio station numbers are. It's the frequency at which, okay, you're listening to those radio waves. And so we're going to see here that our frequency is really how many waves are we going to see in a second, okay? And frequency, wavelength, and energy are all related. We saw that energy is going to be proportional. I know we're going to get lots of letters here, okay? So we've got energy is proportional to and that's going to be 1 over wavelength. So again, instead of an equal sign, we use our little fishy or alpha, and that is going to tell us we have a proportionality. Is it the exact relationship? No, it's just telling us a general relationship here. What's another way to describe 1 over lambda? What is that of lambda? If I put 1 over. Any ideas? If I told you to find the inverse of x, what would you do to x? 1 over. So this is an inverse of wavelength. Okay? And so that means our relationship is inverse. We have an inverse relationship. And again, these are good things to know, generalities for your ACT. All right, Caleb. David, I know you're like, who cares? Caitlin, you're like, who cares? ACT what? But it's an inverse relationship. They're seniors, so they don't have to take it anymore. But an inverse relationship. And really all that means is that so I'm going to put inverse relationship. Let me take this off. That means that as wavelength increases, energy is going to do what? Decrease. Again, am I going to make you know something like that for your test in like that format? No. Do I expect you to know that energy and wavelength is an inverse relationship and as one goes up, the other one goes down? Yes. So why might I even show you that other one? Why would I show you that E alpha 1 over lambda? Is it possible for like the ACT or a future science class to show it that way? Or when you talk in your math class that it may pop up when you talk about proportionalities. It could pop up. So we might as well start seeing those kind of things and get those in our prior knowledge bank. okay, as we go. All right. So here we've got our electromagnetic spectrum. You are going to need to know the spectrum. And I'm going to give you a couple hints of how to remember it. Okay? And again, you are going to need to know that. I like to start in the middle with my visible light because I can typically remember, and a lot of us can remember, the colors of our rainbow. Notice that this is going to go from low energy to high energy. And we're going to talk to Roy G. And now it's just because we got rid of indigo. We just consider it either blue or violet now. But Roy G. And I'm going to put the I. It's just going to be a little I in there. Roy G. Biv. Okay? And if I can remember Roy G. Biv, I should be able to remember the others. Okay? So let's look up this way. Higher energy, is that going to be a good thing or a bad thing for us physically? It is a bad thing, right? Gamma radiation, bad. We don't want to Hulk out. We don't want to be She-Hulk. Okay, it's fictional, but come on. It might be true somewhere. No, but like we talked yesterday and the day before, that gamma radiation is what is killing all of the cancer cells and kills regular cells along with it. We've got x-rays that's also used to kill cancer cells. Again, most radiation therapy is going to be with high energy x-rays. However, they now do brain surgery to remove cancer tumors using a gamma knife. And they don't even have to open you up. They just hit it with gamma radiation and it cuts out that part and really just kills those cells. And then we've got our nice, lovely sunburns. Okay, so what did ultra mean? Do you remember? It means above. So our ultraviolet means above violet in energy. So we're going to start off with our sunburns, then we're going to go to lead vest with x-rays, and then we're going to go to Hulk. Okay? Gamma. And that's one way we can remember that. That's all going to be above violet. Well, below red, infra, you could think inferior, but infra means below. And below red, we have infrared. This says sub-MM. These are really going to be micro waves. Micro waves. They're called microwaves because they have wavelengths around micrometers of a wave. Micro. And then we have radio waves. So as we go towards this end where we have less energy, radio waves, do they really harm us overall? No, low doses, like we're surrounded by radio waves all the time. Now, we talked yesterday about our lovely cell phones and our ear pods. And if they're in our ears all the time, we are getting even more exposure to radio waves than we normally have. And if we put our cell phones in our waist, we have more exposure. And again, especially for young ladies, that's not a good area to have extra radiation, right? If it's in your waistband, with the reproductive organs there, that's not always a great thing. So we don't necessarily know what this added exposure is going to do. Maybe not a lot because it's radio waves, low energy. But again, still don't know. And then we talked about microwaves are a little bit more harsh than that because we don't want to stand around a microwave while it's running. Again, part of that is because early microwaves were not as insulated, like back in the 60s and 70s when they were first made and introduced. It wasn't very insulated. It was new technology. And now they're a little bit more safe and a little bit more insulated and stuff like that. And we know more about them, right? But yeah, I grew up knowing don't stand in front of the microwave. Did I still do it? Yes. Because it happens. Well, and you don't think about it. And if it's only in there for 15 seconds or 30 seconds, you really don't want to move. But yeah, we're not supposed to necessarily put it in there. Okay. And then below infrared we use for heating lamps for our food. Also, there are IR masks, ladies. They're really expensive, but Sam's Club has them right now that you put on your face. Gentlemen, you could do it too. I'm sorry to leave you out, but like it helps like give energy to your face, and it'll help with blemishes and really kill bacteria that you have. Okay. And so we have that. And so that's our electromagnetic spectrum from low to high. And again, I use Roy G. Biv to kind of help me remember what's bad is above, okay is below. All right. Now, this last thing down here, I want to talk about transitions. And again, in order to produce light, here's going to be the full story. We're going to have an electron in what we call an excited state, which means a higher energy level, is going to move to a lower energy level, which is usually called the ground or grounded state. The extra energy, because it's got to lose energy, we got to remove energy to go from a higher energy level to a lower energy level. That bank account, you got to get money out so that your bank account has less money in it, okay? The extra energy leaves the atom as light. Okay, so we have an example of some different transitions for just one hydrogen atom. And again, these electron transitions for hydrogen are what led Niels Bohr to say we had energy rings or levels, that energy was quantized. We can't see electrons in between these energy levels, only at these quantized or specific energies, okay? So a couple of things here. We know that energy level 7 is going to have the highest energy, okay? But energy level 2 to 1 and 1 to 2 has the largest change in energy. A lot of times that is going to be called delta E. Triangle E. I know we're learning lots of math terms today, aren't we? Delta just means literally the change in. Okay, look at the wall for physics. We've got a delta X, a delta X. We've got a delta X, a delta X. We've got a delta V, a delta T. All that means we're taking the final minus the initial. Okay, so here, whatever our final energy is minus the initial energy. Okay, finding that difference or how much it changed. And again, this would be the largest change in our energy. Okay, now, as we get closer to the nucleus, we're going to see more attraction and that means more energy needed to move away. So if I'm close to the nucleus, think about two magnets, okay? If we have magnets that are really close together, is it harder to pull them apart than far away? Find out. Well, okay, Dollar Tree. So I've got these two magnets here. If I'm really close together, oh, and these are oppositely charged. Okay, let me grab another magnet. They have different pulls on the magnet. This one does too. Okay. There we go. So if I have them close together, it's going to be harder to separate those magnets out than if I'm here. It's not hard to move it out further, is it? So the more attraction you have, the harder it is to break them apart or spread them out, okay? And so when we're closer to the nucleus, it's going to take more energy to pull that electron farther out. That's why we have a bigger jump from 1 to 2. It takes more energy. There's more energy associated with it because we're closer to the nucleus. When we get out to energy level 7, that's really far away from the nucleus, isn't it? Is it going to take as much energy to move it from 6 to 7? No, that's why it's smaller in there, okay? So that's why we have those differences in energies of the different levels. It's not an even distribution of energy. It's because of this, that we have more attraction, okay? So that's why we have that bigger space. Now, you're going to notice here that we have some different arrows. What do you suppose the arrows are representing? In our Poggle, what did the arrows tell us we were doing? Yeah, we got to change. The electrons are changing energy levels. And so, like here, we see that we have one going from 7 to 4. One goes from 6 to 4, and one goes from 5 to 4. Okay. We also have this series here, which goes from 7 to 3, 6 to 3, 5 to 3, 4 to 3. Okay. And then we have this one here that goes from 7 to 2, 6 to 2, 5 to 2, 4 to 2, 3 to 2. Oh my goodness, what do you notice is different about this series versus this series here? What's different about our arrows on the screen? These are different colors. And so here we're going to see that this Balmer series is really going to give us our visible light. So we've got our red, we've got our green, we've got our blue, and we've got our violet. And oh my goodness, there's another one. What do you suppose this last one is from 7 to 2? What's above violet? Ultraviolet. That's a UV ray. Okay, so if I have any transition that is going to be bigger in energy from 7 to 2, it's going to be ultraviolet. Which means that pretty much any of these series The Lyman series is usually going to be our UV. So if we end up at N equals 1, we're probably giving off UV radiation. If we're going to energy level 2, we're probably going to visible light for most of that. And if we're going to energy level 3, we're going to be below red, and that's usually some sort of infrared. There's a pretty big range on infrared, and so we're going to have infrared pretty much the rest of our transitions. Infrared to microwaves, okay? Key out of that, energy level 2 usually means visible light. If you go to 1, it's going to be higher in energy, and if you go to 3, it's going to be lower in energy, okay? If you have a transition from 5 to 1, that is going to be bigger than, like, say, 7 to 3, which is 7 to 2. Sorry, I can't add and subtract in my head. But 7 to 2, that's going to be a bigger transition because we're closer to the nucleus. Again, anything that's closer to the nucleus would be higher in energy. All right.